Yes, sir.
So Dr. Bankole taught you guys some parts already, yeah?
Yes, sir.
Yeah. Okay, let's go on. Can you see my cursor then?
Yes, sir.
Yes, sir.
Okay, let's drive. Okay, so basically what I'm going to be teaching you guys is to uncover deep time using clocks in rocks to date geological events. All right. To investigate how these clocks can measure the duration of geologic processes and cycles of Earth's systems. So I suppose I probably will do 3 to 4 classes with you guys just before the exam. Um, so what we want to do today is this first one, reconstructing geologic history from stratigraphic record. Um, so let's start off then. Um, Philosophers have struggled with the notion of time through um, human history, but until fairly recently, they had very data to constrain their speculations. So the first geologic observations pertaining to the question of deep time came in the mid 17th century for the study of fossils. And the question is, what is fossils? All right. So they are the remains of ancient organisms. And there are many types. For instance, you have the natural cast, all right, of shelled invertebrates. You have fish impressions, okay, and you have dinosaurs' footprints, okay. So fossils are the remains of ancient organisms, okay. Well, remember what we're trying to do is we're trying to understand geologic history through stratigraphic record. And for us to do this, we need to understand what fossils means. Okay. So in 1667, Nicholas Tenon, who was working for royal court in Florence, Italy, demonstrated that fossils were the remains of ancient life deposited within sediments. To convince people of his ideas, Stenon wrote a short but brilliant book about the geology of Tuscany, in which he laid the foundation for the model science of stratigraphy, which is the study of strata. Okay. Now, geology uses Stenor's principles to interpret sedimentary rocks, and there are two basic principles from Stenor. That's obvious to us today. We have the principle of original horizontality and the principle of superposition. Okay. Now, the principle of original horizontality states that sediments are deposited under the influence of gravity as nearly horizontal. Okay. Now, observations in a wide variety of sedimentary environments support this principle. If we find folded or faulted strata, we know that its layers were deposited by tectonic events after, or the layers were deformed, sorry to say, by tectonic events after the sediments were deposited. So originally, what you have is, because sediments were deposited under the influence of gravity, you expect that they are going to be deposited horizontally, and after the process of lithification, they become rocks. They will become horizontal beds, isn't it? Now, if you find out that you've got the rocks are faulted or they are folded, it means that they must have undergone deformation. All right. So, for instance, Okay. You have sediments are deposited in horizontal layers and slowly change into sedimentary rock through a process of lithification. Okay. Then all of a sudden, you see something like this in outcrop, right? You should understand that this was not the original orientation why it was deposited. All right. So rocks like this, we will say they've undergone deformation because they are inclined. All right. So this wasn't the original orientation when the rocks formed. Okay. So when we see rocks that are inclined, folded, or faulted, we will say that they've undergone deformation. That's the point I'm trying to make you guys understand. So the first principle is that sediments are deposited under the influence of gravity as what nearly horizontal beds, and that's the principle of original horizontality. Then there's the second principle that says in an undeformed sequence of sedimentary rocks, okay, each bed is older than the one above and younger than the one below. Okay. The rule also applies to other surface deposited materials such as lava flows and volcanic ashes. Okay. So let's take this again, the principle of superposition, which states that in an undeformed sequence of sedimentary rocks, each bed is older than the one above and younger than the one below. Okay, so for instance, in this photo, right, you see these beds here, right? The fact that they were deposited, or the fact that you see them in this position, means that they are older and the ones above are younger in an undeformed sequence. Okay, the beds below are usually older than the ones above, and the ones above are younger than the ones below. If left undeformed or undisturbed by tectonic processes, the youngest layers remain on the top and the oldest on the bottom. Okay. So a chronological ordered set of strata is a stratigraphic succession. We can apply Steno's principle, which is the principle of original horizontality, as well as the principle of superposition in a field to determine whether one sedimentary layer is older than another. At each outcrop, there are distinct formations, groups of rock layers that can be identified throughout a region by their physical properties. Now, by piecing together the relative ages of formations exposed in different outcrops, we can sort them into chronological order and thus construct the stratigraphic succession of a region, at least in principle. However, in practice, there were two problems. Okay. So basically, what we're saying is there are two problems in trying to sort out a chronological order and thus construct stratigraphic successions of a region. Okay. So what are the problems now? The problems are number one is that there is almost always a gap in regional stratigraphic succession, indicating time intervals that had gone entirely unrecorded. Okay, and the second one is that it was difficult to determine relative ages of two widely separated formations. Okay, so the first one is that there is always a gap, and it was difficult to determine the relative age of two formations that are far apart. Okay, now it was necessary to expand Steno's idea about the biological origin of fossils to solve this problem. So we can now see that there were two problems in trying to um, um, determine the relative ages of formations that are widely separated, as well as that there are always gaps in regions, in regional stratigraphic succession. Okay. Now, in order to solve these two problems, we need to think about forces. So that was why we talked about forces in our, I think, our second slide or third slide today. Okay. Now, In 1793, William Smith, a surveyor working on the construction of canals in southern England, recognized that fossils can help us to order the relative age of sedimentary rocks. He observed that different layers contained different sets of fossils, and he was able to tell one layer from another by the characteristic fossil in age. Okay, he established a general order for the sequence of fossils and strata from lowermost to uppermost. Okay, the stratigraphic ordering of the fossils from animal species is known as faunal succession. So this is another principle. It's another principle. Okay, so we now have three principles. So the first, by Stenon, original horizontality. The second, principle of superposition. And the third, by William Smith, is the principle of faunal succession. Okay? Are we together?
Yes, sir.
Yes, sir.
Are you guys following? Yes, sir. Yes, sir. Yes, sir. Where are the ladies in the class?
Yes, sir, we are following.
No, sir, we are not following. Not everybody is following.
Not everybody is following. Who is this person?
Huh?
Who is this person that is not following?
This, I didn't understand what you said in this slide, sir.
Which slide? This one.
Yes, sir.
Where's your name?
Babarinde Sheriff.
What don't you understand? I'm reading the slide and you're saying you don't understand. Can't you read? I don't understand what you said in this slide, sir. 419. Say what?
The law or something like that. This stratigraphic ordering of the forces, that is the third law by William Smith.
Is the third principle we're dealing with. We're talking about faunal succession. And
Okay.
William Smith, what he discovered was that he observed that there were different layers that contain different sets of fossils. And from these different sets of fossils, he could tell one layer was older than another by the characteristic fossil present. Okay?
Yes,
Do you
sir.
understand what I'm saying?
Yes, sir.
He could tell because of the characteristic fossil present in the layers, he could tell that one layer was older than another because of the characteristic fossil. And that's the principle or the stratigraphic ordering of these fossils, right, is known as what? The principle of faunal succession.
Thank you, sir.
All right. Are we still together?
Yes, sir.
Okay. You guys should take this thing seriously. I know some of you just logged on and you walked away. Right? Logged on and walked away.
So we're listening.
Are you sure?
Yes,
You
sir.
can't tell now. You are the one listening. And what about others?
Oh,
We are listening.
Let me see how many people are here.
We are
We are
listening.
listening.
We are listening, sir.
Okay. There are about 50 people here.
We are listening.
Okay, let's continue. Okay. Can you still see the screen then?
Yes, sir.
yes, sir.
Okay, let's
Yes,
drive.
sir.
So we've talked about three principles, right? So what is the principle of faunal succession, right? Groups of fossil animals and plants occur in geologic history in a definite, there are two keywords here, in a definite and determinable order. And a period of geologic time can be recognized by its characteristic fossil. You see these two words, definite and determinable order. All right. Groups of fossil animals and plants occur in geologic history in a definite and determinable order, and the period of geologic time can be recognized by its characteristic fossils. All right, so these two words are quite important because the fossil needs to be definite and determinable. All right, so with these three principles in mind, we can now move on to what we call correlation of rock units. Okay, so we have the principle of original horizontality, we have the principle of superposition, we have the principle of faunal succession. Okay, so let's talk a little bit about correlation of rock units. The method of relating rock units from one locality to another is called correlation. One way of correlation is to recognize the rock type or rock sequence at two locations. Okay, another way of correlation is to use index fossils. The basic understanding of fossils is that fossil organisms, okay, succeeded one another in a definite, you can see this word again, in a definite and determinable order, and therefore a time period can be recognized by its fossil content. Okay, so there are two ways to do correlation. You see that you look at the rock type or rock sequence at two different locations, or you can think about the fossil succession, okay, and say, okay, because I see this fossil here, I see the other fossil there, then I think these rock units are correlatable. Okay, so let's think about it for a minute. If you're thinking about rock types, for instance, okay, let's assume that, you know, we are stood in probably location A, we had some other people standing somewhere in location B, then some other people standing somewhere in location C. All right, because we have the same rock types, okay, in these different locations, we can simply say, you know, image shell is the same as image shell in location B as well as location C, and we can do the correlation just because we're looking at the same rock types. Okay, we can say David sandstone here in location A is the same as David sandstone in location B as well as David sandstone in location C. Okay, the principle of correlation of rock units, right, is just simply looking at the different rock types in different locations and trying to match those rock types as you go along. Okay. Then again, let's look at this schematic. For instance, we have outcrop A and outcrop B. We could say we can see maybe shale here and shale here in outcrop B, and we can say shale in outcrop B, outcrop A is the same shale in outcrop B. Okay, we can do that just by looking at it. But then again, there's a problem because we can't see this limestone in outcrop B in outcrop A. Are you guys following?
Yes, sir.
But we could
Yes,
see
sir.
we can see a limestone here in this sequence, right? But we don't know whether is this limestone here, because just above this shale we could see this limestone, but here we could see shale, we can't see limestone above, but we could see limestone beneath. So it gets confusing when you do this kind of correlation with rock types in two different locations. Okay, so when you see this kind of successions, it get confusing because you could see that things aren't adding up at these locations. Okay. However, we could solve the problem using index fossil to correlate rocks. Okay. So this is the same example I showed on this slide, right? So outcrop A, you could see that you had maybe shale here or siltstone. You have limestone, you have shale, you have sandstone, you have shale. Then you have shale, you have sandstone, you have limestone, then you have sandstone. And it's the same sequence you have here. Okay, so outcrop A and outcrop B. Okay, Now, how do you solve this problem? We talked about looking at index fossil to correlate rocks. Now, fossils formed in some rock layers in outcrop A are the same as those found, right, in some rock layers in outcrop B, some distance away. So you could see that these fossils here in this stratigraphic unit are the same fossils found in this stratigraphic unit in outcrop B. Okay? Layers with the same fossils are the same in age. All right? Because we know that we found this here in outcrop A, and found this here in outcrop B, so same fossils, we can safely say that this rock unit is the same as this rock unit in outcrop B. And once we do this, right, we could say everything below this unit here, right, will probably be of the same age as everything here, but it could be that some units are missing here. So for instance, this limestone could be missing here, okay? Then if we do that, we can safely piece together, right, all of this information and create a complete stratigraphic unit looking at this fossil succession. So for instance, we could say that since these rock units are the same, so unit 2 as this unit 2, so unit 2 in outcrop A is the same as unit 2 in outcrop B, we could say this is unit 2. Okay? Unit 2. All right? And we could pick this unit 3 as the underlying succession. Okay? Unit 3 as the underlying succession. And we could pick everything above, right, as unit 1. Just because we know the fossil content of outcrop A matches that of outcrop B in this unit 2, we cannot pierce everything together and create a sound stratigraphic succession of the outcrops. A composite of the two outcrops will show formations 1 and 2, both overlying formations 3, and therefore younger than formation 3. Okay, so this is all that we know. And this formation. Are we following?
Sorry, excuse me, sir. Can you please come again?
Yeah, so what are you guys saying? You said what?
Can you please explain the cross section of the arrangement, please?
7.
All right. Did you say I should go over this again?
Yes, sir.
What don't you understand? Let me know.
I understand relating the fossils, but like the image by its side, the cross section, I don't understand it.
Okay. So on this side, on outcome A, you could see unit 1, right?
Yes, sir.
And you could see unit 2.
Yes.
On this side of outcome B, you could see unit 2 and unit 3.
Yes.
Now let's assume there were no fossils. Okay, let's assume we don't know anything about the fossil content of these rock units. All right. If you were given these two outcrop units to correlate, right? What you're going to do basically is to look at this limestone and say this limestone, right, is the same as this limestone here. Right? At first pass, that's exactly what you're going to do. I think this limestone is this limestone here. But there's a problem because I can't see this sandstone above this limestone here. All right. Then I can't see this shale below this limestone here. But I could see a shale, but what's just immediately beneath this limestone is a sandstone, but it's a shale here. So it gets confusing. All right. Using rock types. And that was what I was trying to make you understand that, okay, if you simply use rock types, right, you're going to run into problems. You're going to run into problems because you're using rock type. So this is the same figure, but in 2D, not in 3D. What I'm saying is that you're going to say unit 3 is the same as unit 1. All right. So you take this a little bit and you correlate, okay, I'll draw this line here, I'll draw this line here. These two units are the same. But in reality, they are not. Because it means if you correlate this with this, you are missing this unit 2. You cannot correlate this unit 2 across this limestone here to unit 2 here. We know this because we can simply look at the fossil content and do a correlation. And once we've done that this unit 2 is the same as this unit 2 here, we can safely say everything beneath unit 2 is unit 3 and everything above unit 2 is unit 1. And that's why you have unit 1 here, younger than unit 3, that's older. Because we know the fossil content within unit 2, and we can say the unit 2 is the same unit 2 here because we know the fossil content. Then we begin to arrange things because we already know what units. So these units are above unit 2, and these units are below unit 3, below unit 2. Okay?
So I have a question.
That's why we came up with this succession. Yeah, what's the question, please?
So on your outcrop A, if we are to correlate them based on fossil content, now the fossil B below it's what I call it, limestone, and below fossil A is shale. So how can we now talk about?
Sorry, I didn't get that. Please, can you repeat yourself, please?
You said if we correlate these fossils based on fossil content, it
Yeah.
shows that everything below that shale, below limestone downward is below at the subsurface. Now,
Yeah.
if we check outcrop A, below that part that is related, that is having the same fossil record with fossil B, below it is shale. What can you say about the one below and this other side to below both outcrops? Because there are different contents in them.
Yes. So if you look at unit 2 here, all right, unit 2, right, you could see you have shale here, you have sandstone. You have shale, you have sandstone. Look at unit 2 here. You have shale, right? You have sandstone, right? Then you can put this limestone here. What I'm saying basically is that we already know that unit 2 in outcrop A is the same unit as outcrop B, because we know the fossil contents. Now, if you say outcrop B, you only have unit 2, you don't have unit 1. We can just simply dump unit 1 across and say we think unit 1 was here. All right. And here, because we see unit 3, we can say this unit 3 was here.
Hello. Next one.
Sir, you muted.
Okay, that is my name. You are muted, sir.
Hello, can you hear me now?
Yes, sir.
Yes, sir. Yes, sir.
I don't know. Do we understand this stuff at all?
So I don't understand. I think the thing confusing is the unit 3 because of the shale and the limestone. Unit 1 and unit 2 is understandable.
Let me tell you something. We can begin to interpret this geologically that it was possible, right, that unit 3 was somewhere in outcrop A. However, it has been eroded away. So what we see now, right, is this unit, sandstone and shale, but unit 3 is not here anymore. But if we don't use the fossil content of this rock units, my point is it's going to be difficult to correlate these rock units because they are far apart. All right? They are far apart, so it's difficult for us to correlate. But because we now understand the fossil content, we can begin to piece together the information and say, okay, we know we have unit 1, we have unit 2, and we have unit 3. And everything below unit 3, let's assume is unit 4. This is unit 4. This is unit 4. But yes, unit 3 here, we don't know. But as geologists, we can say unit 3 was here before, right? But it's been eroded away. And that's an interpretation. But we know unit 1 was here. We can't see unit 1 here. We can safely say unit 1 was eroded away here. All right? Unit 3 was eroded away from unit 2, from outcome A. Just because we can now know that unit 2 is the same unit 2 here because of the fossil content, we can begin to do our interpretation when we pair the rock unit together. That's what we're saying.
I have a question.
What's the question, please?
Sir, from what you are saying, it means the bottom layers too can actually erode as well as that of the surface too.
Absolutely, absolutely. So in
Okay.
time past, right? So think about the principle, one of the principles I told you, principle of superposition. Rocks above are older than rocks below, right? But remember, these rock units or outcrops, they are far apart, all right? So probably, right, geologic conditions in outcrop A favor the erosion of unit 3. But in outcrop B location, it didn't, so it was preserved. Okay? And that's why you can see it in outcrop B, but you can't see it in outcrop A. Now, what is making us do all of this correlation is because we already understand the fossil content in unit 2 in outcrop A and outcrop B. Okay? Now, look at the fossil content again in A. For this unit 1, obviously, we can't find a unit. We can't find it in unit in outcrop B. Okay? For unit 3, we can't find the fossil content. Look at the fossil content here. We can't find it in outcrop A. So just because we can't find it, it will be safe for us to now say, on this stratigraphic succession, we have outcrop 1, right? Outcrop 2, and outcrop 3. Why are we not putting this outcrop beneath on this succession? Because we are not sure. Why are we not sure? We don't have the fossil content. That's why we're not putting it below. We are not sure. We don't just want to say this unit is the same as this unit because we don't have the fossil content. Remember, the principle of faunal succession states that fossils, they succeed themselves, right, in a definite and determinable order. Look at these units, all right? Look at the fossil contents, right? You could see that the fossil contents, even though they overlap, right? They overlap, right? But we're pretty sure that this fossil content is younger, no, is older than this fossil content. And this fossil content, right? This fossil content is older than this fossil content. I don't know whether you guys understand what I'm trying to do here.
Okay, sir. So, okay, but what you're trying to say now is that the limestone part in outcrop B,
Yes.
if you try to look at it in outcrop A, it has been washed off or it has been eroded away.
Use the word, use the eroded, not washed off. Are you washing off? Are you?
It has eroded away.
Yes.
So definitely, since we don't have any information about that, so we put the limestone as the other rock on the outcrop B.
Yes, because we know the fossil content.
Okay.
Because remember the principle of faunal succession, they succeed themselves in a definite and determinable order. So we can safely say that this fossil content, you can see my cursor. Can you see my cursor?
Yeah, yes, sir.
This fossil content is older than this fossil content. And this fossil content is older than this fossil content.
So we
Okay.
match them together.
Good. So we can begin to pair them together and the rock units. So what's making us say unit 1 overlies unit 2, overlies unit 3 is because of the fossil content. Not because of the rock type. Because the rock type could be deceiving. So what I'm saying, there are two ways to do correlation. You could use rock types, but rock types could be deceiving. What we can use to save us of that mess is using index fossils. And I'm going to talk more about index fossils now. But just know that we started with principle of original horizontality, that rocks are initially laid down in horizontal manner or orientation. The second principle is rocks below are usually older than rocks above. And the third one is the principle of faunal succession, right? That fossils, they succeed themselves in definite and determinable order. And we can now use all of this information to begin to do correlation. Are we still together?
Yes, sir.
Let's drive on there. So this previous slide talks about index fossils to correlate rocks. Now, what's the meaning of index fossil? A good fossil or a good index fossil is one with 4 characteristics. Number 1, it is distinctive. Number 2, it is widespread. Number 3, it's abundant. And number 4, it is limited in geologic time. Okay? Look at this succession from 1 to 10, all right? Looking at these fossils within these rock units or successions,
Sir, are you
You are
there?
muted, sir. You are muted.
have we studied the fossil contents? So look at the fossil content. You could see that there's some overlap. You could see this one here. You could possibly see this one's in unit 3. You could see, this one goes all the way to unit 5. You could see this one, just within unit 5. You could see this one goes all the way to unit 6, unit 8, unit 9, unit 10. You could see this one 8, 7, 6. You could see this one within unit 3. Now, think about the characteristics of index fossils. It is distinctive. So all of them are distinctive, isn't it? Can you see that they are unique in their own?
Yes.
Yes, sir.
Right? Are they widespread? We can't necessarily tell that they are widespread from this figure. All right. Are they abundant? Sort of, they are, right? The key distinguishing factor in this particular figure is that it is limited in geologic time. All right. So the index fossil is this kind of invertebrates or something, right? And why we're calling this the index fossil is that it does honor this characteristics, which is it is limited in geologic time. And if you look at this figure, you could see that this fossil spans, you know, 1, 2, 1 and 2. This one spans 2 and 3. This one spans where is it? You know, okay, there are only 3 fossils here, A, B, and C. All right, and on here, right, they are picking this as the index fossil because it's just limited within a small geologic time. Now let's forget this one and look at this one. The index fossil for this succession is this invertebrate here because it is limited in geologic time. Now, because most fossil-bearing rocks formed in the ocean, the major index fossils are marine fossils. But certain land organisms are useful in young rocks and in specific regions. I want you to note this. I want you to note this. Also, I want you to note these characteristics. It's quite important. Okay? Going forward. Now, the geologists who followed Stennon, Nicholas Stennon, and William Smith's footstep described and cataloged hundreds of fossils and their relationship to modern organisms, establishing the new science of paleontology, which is the history or the historical study of ancient life forms. Geologists did not find fossils in intrusive rocks, all right? And that's no surprise, basically because biologic materials would have been destroyed in hot melts, talking about intrusive rocks. And they also did not find fossils in highly metamorphosed rocks. For same reasons, because those fossils would have been distorted, all right? By the beginning of the 19th century, paleontologists had become the single most important source of information about geologic history. Are we still together?
Yes, sir.
Yes, sir.
Okay. So we've talked about 3 principles. We've talked about correlation of rocks. We've talked about index fossils, talked about their characteristics, right? And now we're moving on to unconformities. Unconformities, right, are simply gaps in geologic record. In putting together the stratigraphic succession of a region, geologists often find places in the geologic record where information is missing. Just like you saw in that example I gave you, where we didn't find the limestone in outcrop B, right, in outcrop A. Either it was never deposited or it was eroded away before the next strata were laid down. The boundary along which 2 existing formations meet is called an unconformity. Now, an unconformity, although we said it's a gap in geologic history, but in reality, is a surface between two layers that were not laid down in an unbroken sequence. So an unconformity keyword is a surface that were not laid down in an unbroken sequence. When layers of rocks formed without interruption, we call them conformable. Conformable. All right. So let's think about this figure here. All right. We are trying to resolve the past, right? And in time one, we had unit A, unit B, unit C, unit D deposited in that sequence. All right. Then all of a sudden, right, in time two, right, we had tectonic forces causing uplift of the beds above the sea, all right, and exposing, right, some of these layers because of the tectonic forces. There was uplift. And we had unit D exposed, all right. And of course, when you expose unit D, the next thing you expect is that you have the agents of erosion acting on unit D, and you have unit D eroded away. Okay. And due to that erosion, you're going to leave an irregular surface, all right, and so some part of unit C preserved. Then in time 4, we have subsidence, okay, below sea level, and we had unit E deposited directly on unit C. All of a sudden, what do we have next? We have a surface, right, that is termed an unconformity that represents the gap, right, in geologic history. Because, of course, we had unit D eroded away, right, by the agents of erosion. Remember, there was uplift, there was exposure, and there was erosion, right? We lost unit D, and when there was subsidence and deposition of unit E, we had this surface preserved, which is now the unconformity, and it's a gap in geologic history. So an unconformity is always a surface. So for instance, in the exam, if I ask you what is an unconformity, I want to see someone writing something like an unconformity is a surface that represents, all right? Are we still together?
No, sir, please come again. Sorry, please come again, sir.
I'm not coming anywhere. I'm not even coming anywhere again. Don't give me a headache. What can you understand here, this man? Come again, come again, come again. Where are you coming again? I'm not coming again. I'm going forward. Are you still there?
Yes, sir, I'm still here, sir.
Who are you?
Uluwadara, sir.
Oluwadare. Oluwadare.
Uluwadara.
Oluwadara.
Yes, sir.
Okay. Look at time 1, right? We had A, B, C, D, right? Time 2, what happened? There was an uplift, right? We had unit D exposed, right? And we had the agents of erosion, weathering, all of that, transportation, and all of that. They worked on Unit D and they finished that unit and they started entering Unit C, and that's what you have here. All right. So we had Unit D stripped away, part of Unit C as well, right? And we had this irregular surface. And there was now subsidence, right, after these geologic processes, right? And we had sediments coming in, right, being litified, forming Unit E on top of Unit C that was almost eroded, okay?
Yes.
What we're saying now is that there was this irregular surface, and this irregular surface is now the unconformity we're talking about, because it's a surface that represents a gap in geologic history. Okay, if you go back one, what I'm saying is that the boundary along which two existing formations meet is called an unconformity, which represents a surface between two layers that were not laid down in an unbroken sequence. So these two layers, right? If you go forward, these two layers were not laid down in an unbroken sequence, but these layers, right, were laid down in an unbroken sequence. But this surface represents a gap in geologic history because they were not laid down in an unbroken sequence. I don't know if you understand that. I don't know how else I need
I
to
understand now, sir.
Do you understand now?
Yes, sir, I do.
Can I move forward then?
Yes, sir. Thank you very much.
You are welcome. Having established that an unconformity is a gap in geologic history, the next thing is we need to think about the types of unconformity that we have. Okay? And in doing so, we need to think about the relationships between the upper and the lower sets of layers. So, in order to establish the types of unconformity, we need to think about the relationship of surfaces like this. What relationship with E and D? That's how we know the types of unconformity that we have. And basically, there are three types of unconformity. There are angular unconformities, we have disconformity, and we have non-conformity. What is an angular unconformity? An angular unconformity consists of a tilted, folded sedimentary rock that are overlain by younger, more flat-lying strata. Indicates a period of rock deformation and erosion. This is an example. Originally, these beds were deposited horizontally, principle of original horizontality. Okay? And in time B, we had compressive forces acting on these rocks, causing folding and uplift. All right? Then all of a sudden, in time D or C, we had erosion, just like the previous case we talked about, right? Of this crest, right? And in time D, we now have deposition. Right?
Hello. Hello.
It's like you guys are not you guys are not even bothered. If I'm not talking, you guys are not bothered. You are just, I think you guys are playing.
No.
I thought maybe your connection was bad. That's why I was saying hello, hello. Sorry, sir. We are following.
You are not, some of you are playing. I can see you, some of you are playing. We have 49 people here. You can't even remember your faces anymore. Giwa,
Sir.
are you there?
Yes, sir.
Sorry, but I don't even know these people in this place. Rane. Rane is not there. I thought I saw one dead piece. Peace.
Good morning, sir.
Okay, you are there. Uno room.
Good morning, sir.
I can see you. Vanessa.
Good morning, sir.
Okay, all of you are there. Elizabeth.
Good morning, sir.
All these bad boys in the class, I don't even know themselves. ABI.
Good morning, sir.
All of you be hiding. Ajo Moses. Are you there? I get.
Yes,
You know what I'm thinking. Some of you will just log on. Then you go to the kitchen to carry food. Muid.
Sir,
That one is not there.
I'm here, sir.
I wish I could see your videos. So I know some of you will probably be hanging somewhere. Jatu.
Sir.
Obina.
I'm here.
You are where?
My house.
Sheriff. That one is not there.
Sir?
That one is watching movie. I caught him. Oh, Abraham.
Yes, sir.
Yes, sir. I strongly believe that you guys are following this lecture.
Yes, sir. Yeah.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Silas. Okay, no wala. Let's continue. Okay. So we understand angular conformity, right? So the angular conformity, right, is the surface. And what is happening here, right? Basically, right, is separating these deformed layers below from this undeformed layer above, sorry. And you can see that when you go back one, indicates a long period of rock deformation and what? Erosion. And here's a typical example, right? And this place is called Sika Point. It's quite unique, all right? And it was described by James Hutton more than 200 years ago in southern Scotland. Basically, you could see that these beds are nearly vertical, and you could see these beds are nearly horizontal above. So basically, where is the unconformity? The unconformity is this surface. I don't know if you guys can see this actually. The unconformity is this surface. It's a surface that separates, right, this deformed layer that is nearly vertical from this undeformed layer.
I have a question.
Yes.
This is Elizabeth. I just want to know if the unconformity can tell us the rock that was eroded. Is it possible that the unconformity tells us maybe the type of rock that was eroded before the deposition of another layer?
Of course, now this one below is the one eroded now.
Okay, sir.
I don't understand your question. You know, an angular unconformity consists of a tilted or folded sedimentary rock that was overlain by a younger, more flat-lying strata. So, of course, the unconformity I tell you, right? Which rock was deformed, right? Because we already know that rocks above are usually younger than the rocks below. So it could be that these were deposited originally as horizontal rocks, but after deformation by tectonic forces, right, they became nearly vertical, and these rocks, right, were now deposited after erosion of this bit here.
I understand.
Do you understand?
Yes, sir.
Okay. Can I go on now?
Yes, sir.
I'm going. Disconformity. A disconformity is a minor irregular surface separating parallel strata on opposite sides of the surface. A disconformity is a minor irregular surface separating parallel strata on opposite sides of the surface. It indicates a history of uplift above sea level, right, undergoing erosion, and lowering below sea level again. Let's think about it. On this one, basically, there's no deformation. In time one, we had the succession being deposited, And all of a sudden, we had exposure of this layer, right? And because it was exposed, it was now eroded. Okay. Then subsequently, we had deposition of another layer on top. Okay. Now, we're saying it's an unconformity. And this kind of unconformity, right, it's a surface that represents a gap in geologic history. But in this case, the underlying rock was not eroded, right, or was not deformed, I should say. Basically, the disconformity separates parallel strata on opposite sides of the surface. However, there's been an erosion. All right, that's why it's called an unconformity. And this kind of unconformity is a disconformity.
Sir, question.
Carry on.
So that was why I asked the other time that how would the unconformity tell us the rock that was actually eroded? Like the first diagram showed that there was water and there was sandstone. Then there was regression, the water moved backward, then sandstone was eroded totally, and we have Devonian left before there was now deposition of sandstone again and Jurassic. So how would the unconformity tell us that sandstone was actually eroded before we have another sandstone and Jurassic deposited on the layer? That's my question.
Okay.
You understand?
Okay. We talked about what just now. Can you remember index fossils, right?
Yes, sir.
What are the characteristics of index fossil?
Definite, abundant, determinable, and must occur within a limited geological history.
It's me that told you all those things.
Must occur within a limited geological time.
I gave you 4 characteristics. What are they?
Oh, okay. Number 1, it must occur within a limited geological history.
Yes.
Must be abundant, widespread, and definite. Yes.
Good. Good. Now think about it, right? If you had index fossil here, in this unit that looks like maybe shale, then this conglomerate, then probably in this maybe what would I call this now? Let's call it another unit anyway. If you date these rocks, or you look at the fossil contents, and you know the fossil, the ages of the fossils, okay, you can almost tell that, all right, there's a unit missing before Jurassic. All right, before Jurassic. Do you understand what I'm saying?
Yes, sir.
So dating can possibly tell you that you cannot move from Devonian to Jurassic. Okay?
Okay.
You had Carboniferous missing. You possibly had Permian missing. You had one other unit missing before Jurassic. You cannot move from Jurassic to Devonian. Okay? You cannot possibly move from Jurassic to Devonian. You had maybe Triassic, Permian, Carboniferous, you know, missing before Devonian.
Okay.
So by simply using
age
index fossils, remember the exercise we are doing just now, where we're looking at outcrop A and outcrop B.
Yes.
All right. So let's go back. Look at this kidney here now. Let's assume that what we're looking at just now was we had maybe this is Devonian, right?
Okay.
And this is what?
Jurassic.
Jurassic, right? What we have here, right?
Yes.
What we have here is something here. So this right?
Mhm.
No, let's come here.
Yes.
This will probably be what?
Devonian.
No.
Nonconformity.
An unconformity. Do you understand? Simply because we've dated the rocks using the fossil content.
Okay.
So going back to your question, right? The unconformity cannot necessarily tell us the rock units missing, except we date the rocks using the fossil content.
All right. Thank you, sir.
And that's in the case of what? Disconformity. But in angular unconformity, right?
Yeah.
When we see it in the field, we will know because the underlying unit has been deformed and the underlying unit is almost flat line, right? So we can put our finger on there and say, this is unconformity because we can see the relationship between the two rocks above and below the surface. But in a disconformity, it will be difficult except to get the rocks. I don't know whether you understand what I'm saying.
Understand, sir.
So in this case, it's easy to know. We can put our hand on this surface and say, this is an unconformity. We are pretty sure that there were some rocks above here that were eroded before this was deposited. However, in this case, right, let's say you were here, we were looking at this place here. It's difficult to tell that there was an eroded piece here before this was deposited.
Yes.
All right?
Yes.
It's difficult to tell. Disconformities do not show angular discordance, but an erosion surface separating the two rock bodies. Now, the channel in the central part of the outcrop reveals that the lower shale units were deposited and then eroded before the upper units were deposited. So if you are looking at this picture, you will know that it's difficult to tell except you date it. But if you see this kind of relationship, this is a channel. This is a channel eroding into this lowermost units. But let's say we didn't have this luxury of seeing this kind of relationship, and we are stood here and we look at this, it will be difficult to tell what happened here because it's a disconformity. I don't know if I've answered your question, but
Yes, you have, sir.
okay. Can I move on now?
Yes, sir.
Okay. And there's the third type. So we've talked about angular unconformity, we talked about disconformity. So now let's talk about non-conformity. A non-conformity is a break surface that develops when igneous or metamorphic rock were exposed to erosion and younger sedimentary rocks were subsequently deposited above the erosion surface. That's straightforward, isn't it? So you have intrusive igneous rock, you have sedimentary rocks above. So you have erosion here, right? And you have deposition of sedimentary unit above this granite. Okay, so it's straightforward. I don't need to explain this one. This one is straightforward. Okay, it's exposure, erosion of granite, the deposition of sedimentary rock. So this is a non-sedimentary rock underlying a sedimentary rock. Okay, note there must have been an exposure, weathering, and erosion and deposition of a sedimentary rock. So you cannot just see this and say this is an unconformity. All right, when there's no erosion. Okay. Again, in outcrop, this is what it looks like. Sedimentary rock overlying Okay, metamorphic rock. Okay. So distinguishing non-conformity and intrusive contact. Non-conformity, the sedimentary rock is younger. The erosion surface is generally smooth. Dikes may cut through the igneous body but stop at the unconformity or the non-conformity. Intrusive contact is younger than the surrounding sedimentary rock. The contact surface may be quite irregular. A zone of contact metamorphism may form surrounding it. So we are just trying to distinguish basically the difference between non-conformity and intrusive contact. And exactly this is what we're saying. So this is non-conformity, okay? And this is an intrusive what? Contact. So know the difference. I was going to leave you guys with this story, right? But okay, let me still leave you guys, all right? What I want you to understand is that we had, maybe most of you that are curious enough, you know, you must have read something about Grand Canyon. All right. So look at this. This is Grand Canyon sequence. All right. We have, can you guys see this?
Yes.
We have location A, location B, location C. Location A is called Grand Canyon National Park. B, National Park. Canyon National Park. All right. So this is Utah. This is somewhere in the US. Okay.
Arizona.
Arizona. Arizona. We've gone to the US before, but Arizona. Arizona. Let me teach. Can I teach?
Yes, sir.
Yes, sir.
All right. So what happened? So take this as your location A, B, and C, right? The rocks of the Grand Canyon and other parts of Colorado Plateau have many stories to tell. All right. So this is to cap our lecture up today. They record a long history of sedimentation in a variety of environments, sometimes on land and sometimes under the sea. From correlation of the rock sequence exposed at different localities, geologists can reconstruct the geologic history over 1 billion years long. Okay. So those two locations I showed you basically, or three locations, right? They are kind of, they are really far apart actually. And what we have is, so we have location A, location B, location C, all right? And we have various formations, all right, in these different localities. And this is geologic time scale, all right? So we had Devonian, Jurassic, down to, Paleogene, all right? And somewhere in the Precambrian, we had this rock sequence that was deformed, basically, by tectonic processes. And we had some rocks that were tilted, all right? And subsequently, we had rocks that were deposited horizontally, honoring the principle of original horizontality. Then when you go to location B, right, we had same, more or less same process happening, deposition of different rock formation, then location C as well, deposition of different rock formations. Okay. And how are these correlated? By looking at fossil contents within these rocks, we could possibly date the fossils that were preserved during the Permian here and here. The fossils that were preserved, within this period, Jurassic and Triassic, were found here in this location and here in this location. And then geologists were able to piece together, right, this formation. So these fossils were unique, right, within this time frame. These were unique within this time frame. There was an overlap between these two locations, and there was an overlap here within these two locations. So doing the correlation of these rock units using index fossils, they were able to piece together, right, how, these rock units correlated from location A to location B to location C. All right. The correlation of strata among these three areas of the Colorado Plateau shows how widely separated localities, each with an incomplete record of geologic time, can be pieced together to build a composite record of Earth's history. Going back to what we said earlier, without the information of index fossils, one can possibly say the sandstone, Navajo sandstone, is the same as the Coconina sandstone in location A, as well as the Dakota sandstone in location C. So geologists were able to do this kind of correlation by looking at what? Index fossils. That brings us to the end of the class. Any question?
Yes, sir, I have a question. Sir, in some cases, as part of the type of unconformity, so it usually puts that paraconformity usually put together. That is making it 4 types of unconformity. But now I wanted to know the difference between paraconformity and disconformity.
Between what?
Hello, sir. I wanted to know the difference between paraconformity and disconformity.
There's no difference.
Okay, thank you, sir.
Sometimes people say there's a difference, actually. Okay.
Okay, no problem, sir.
Sometimes people say there's a difference, but me, I see no difference. So take it from me, there's no difference.
Okay, thank you, sir.
A paraconformity is a disconformity too. All right. So there's no difference.
Hello, bro.
Who is this? Who is this person? Hello, bro.
Eh?
Who is that person? Who is that comedian? Hello, bro. Who is that person? This man, who asked me that question?
Francis.
Who asked me that question? Yeah, so a paraconformity basically is a disconformity. I don't see any difference. Most times you know, like this example I showed you, right? When you are here, you can say it's a paraconformity because it will be a flat surface. Can you see my cursor?
Yes, sir.
It will be a flat surface. But here you are seeing that it has eroded, there's a channel. All right. So just take it that a paraconformity is a disconformity. No, I won't ask you any question on that, but know that it's a disconformity. It's a non-conformity, but it's a disconformity, right? But
okay, sir.
It's more or less like a conformity that is not very obvious. You understand? It's not very obvious. So people will say we can't see it, but if you date the rocks using index fossils, you will know that there's a non-conformity there. All right. So assume that the paraconformity is a non-conformity. So when you are here, you probably will not know, but when you are here, you will know because you can see the shape. There is a channel intruding these underlying rocks. Okay. Okay. That brings us to the end of the class. Now, another question, please.
Sir,
Yes, sir.
What?
I did not get your explanation on this Grand Canyon. I got disconnected.
Who is that?
ABI Eru.
Where is disconnecting you?
I don't know. This is Nigeria.
Oh, I thought I was in Europe. This is Nigeria. You read it up now. Why you do you want me to repeat myself again? Read it up.
Sir, please, can you repeat yourself? Because I've been checking that license you sent it and I'm really not getting what to say.
So you
So
want
I
me
was
to
really
go over
hoping
this?
to hear your
You
explanation
want
on
me to
this.
go over? You want me to go over all of these things again? Who is with you on this? ABI.
Sir.
Listen carefully.
Okay, sir. Thank you, sir.
So I was saying that look at this map, right? Imagine the scale on this map. All right, you probably be looking at a scale within maybe 100 kilometers or thereabouts between location B and C, and you probably be looking at maybe 300 kilometers between A and B. And I was saying that if you've got this kind of widespread localities and you're trying to do a correlation, simply looking at rock types won't help you, because you could possibly say the Navajo sandstone is the same sandstone as the Dakota sandstone. Or you can even say, because it's of the same thickness, the Navajo sandstone is of the same thickness with this straight cliff sandstone, all right, then they might probably be the same units. Or the Coconino sandstone in location A is the same as the Navajo sandstone. Or the Wingate sandstone, for instance, in location B, just looking at rock types and the thickness of the rock types. If you did that, you'll be absolutely wrong. But using index fossils, geologists were able to basically look at the ages of the index fossils, all right, and their characteristics to say that the Kabbab limestone is the same limestone as you have in location A and location B. Then the Navajo sandstone, right, is the same sandstone as you have in location C as well. If these rocks were safely dated, geology can be able to piece together the rock unit from Precambrian down to Paleogene, because they know that fossils succeed themselves in a definite and determinable order. And doing that, they were able to piece together, right, the correlation between location A, location B, as well as location C. All right. Remember, these locations are widely separated, and each had an incomplete, right, record, right, of geologic time, as you can see on this figure here. You could see that in this location, it was incomplete because we stopped at Triassic. In location B, we stopped at Jurassic. And in location C, we got all the way down to Paleogene, but we didn't have rocks that were represented till the Precambrian. So we had incomplete records at these different localities. All right. But looking at it today, geology was able to piece together like the correlation, because they had information about the characteristic index fossils that succeeded each other in a determinable and definite order. And they were able to come together, right, the composite record of Earth's history in this locality. Do you understand it now?
Yes, thank you, sir.
You are welcome. Any other question, please? I think I'm done. I'm tired, man. I've been talking for about 2 hours now. All right.
Yes, sir. Thank you, sir.
In reality, you can't have someone's attention for 2 hours now. Okay. Now, just to leave you guys with this. Okay. So I basically, right, gave you an exercise to do. Have you guys done that?
Yes.
Yes,
If you
sir.
do that by 3 p.m. today, right? I want you to upload it, what you've done. Put your math number on it. All right. I'll talk to you guys by 3 p.m. today. Put your math number on it. I'm going to set it up in LMS, right? Upload what you've done and give reasons why you've chosen, right? What you've chosen.
Yes, sir.
By 3
So
p.m., upload it on your LMS.
you submitted it already.
Have you submitted?
Yes,
Yes.
sir.
All of you?
Yes, sir.
No, sir.
Not all have submitted, but most of us have submitted.
For those that have not submitted, 3 p.m. is the deadline today. So try and submit.
Okay, sir.
I'll talk to you guys same time next week.
So
For
what
the,
is that, sir?
who is this one? Who is this person? They're asking me what assignment is that. I don't want to just don't ask me that kind of question, please. For the geophysics students, I'll see you guys tomorrow 9 o'clock. Giwa,
All right, sir.
have I sent the link? Giwa?
No, sir. You have not sent the link.
Okay, I will send it to you. All right, then. Bye for